Okay, so we're going to be doing part one of two of integration by substitution. I think this is quite a nice integration method. Maybe it's a bit less scary than something like reverse chain rule. With reverse chain rule, you have to use a lot of intuition. Integration by substitution is a lot more methodical and just a case of applying the principles as they, you know, as they should be, right? You don't have to sort of be guessing so much. There is an element of guesswork in terms of what your substitution should be. So that we'll talk about a bit more in part two. But I think for part one, I'm mainly going to be focusing on can you do the calculation correctly? So you'll be given what the substitution is in each case. So on the topic of substitution, just to clarify what I mean by this, simply what you'd usually expect it to mean, which is you have an expression or a variable and you replace it with a different variable or a different expression. So to just get into the swing of things, what I have here on this slide, it's not an integration question at all, but it is a question that requires you using a clever substitution. So you can definitely answer this question. I think you've done stuff on this topic before, but I'd be interested to see if you remember how to do it. There's one specific substitution you need to find. So see if you can do it. You've got this equation here. The number 1 definitely works. 1 to any power is 1, so this is 1 plus 2 equals 3. And there's exactly one other real solution. Can you figure out what it is? You can give it a go. Pause now. Okay, so the substitution, in fact, let me just give you the substitution first. The substitution you should use would be change x to the 11 to be a new variable. Let's say little u. If you didn't already try it, I would suggest definitely still pause it now and try and use that substitution to solve it. Otherwise, let's take a look. So this equation here can be rewritten then as u plus 2u to the minus 1 equals 3, if u is indeed that substitution. Multiply both sides by u, and we get this, which looks a lot like a quadratic, because it is. And then we can factorize this into u minus 2 and u minus 1, which implies that u equals 1 or u equals 2. And then that implies that x must be the 11th root of 1 or the 11th root of 2. Now, the 11th root of 1, that's just the number 1, which makes sense because that was one of our solutions. And the 11th root of 2, that's just some strange decimal number. So this is the other thing we were looking for. And in fact, that is the answer. It's the 11th root of the number 2 is the solution to that question there. So the principle being demonstrated here effectively is you can have a question which looks complicated or difficult, and by using an appropriate substitution, you can then use methods that you already know about, in this case quadratic factorization, to solve it. So extending that principle to integration is what we're going to do. We're going to have integrals that we don't know how to integrate, but by using a substitution we can turn it into a form that we do know how to integrate. And there's only one other thing we need to consider when we're doing that, which relates to this change of variables. So that wording, change of variables, I will explain in a moment. Let's take a look. Okay, so here is our integral. The integral of x times root 2x plus 5 with respect to x. And funnily enough, there's actually two possible substitutions being suggested here to solve this. I think this is mainly to just illustrate that ultimately there's not always one magic substitution that you might want to use. There could be multiple that work. The name of the game is ultimately take an integral you can't integrate and turn it into one you can. Okay, so I'm going to just demonstrate the method for how this works, and I think, having seen it a couple of times, it'll become quite clear. So first of all, let's just fully write out the integral one more time. So it's this, okay, and the tricky thing about substitution, well, not that tricky, but the thing you've got to watch out for is we're about to change all of these x's using that substitution into u's, or expressions of u's. But the problem is this integral is with respect to x. So that's going to create an issue, but we're going to fix that in a moment. Let's just try and do the substitution first. So first of all, if we're using this one, u equals 2x plus 5, we're going to get the integral of x times the square root of u dx. But I don't want a mixture of letters. I want it to either all be x's or all be u's. In this case, I want it all to be u's. So this x that I have here, that I also need to turn into u's. So let's just rearrange that, okay, which shouldn't be too hard. So x is equal to u minus 5 divided by 2. Yeah. So now I've got the integral of u minus 5 over 2 times the square root of u, which I'm actually just going to call u to the half dx. Okay. So this integral, it's looking closer to something we could integrate, but dx is the problem. So here's how we fix it. Consider your substitution and take the derivative of it. So I'm going to work over here actually. U equals 2x plus 5. Take the derivative of both sides with respect to x. So on the left, I'll have du over dx. U with respect to x is du dx by definition. And the derivative of 2x plus 5 is just 2. And then what I'm about to write is called an abuse of notation. We're going to almost pretend that this is a fraction, and we can actually write the following, which doesn't really have that much meaning, but I'm going to show it to you anyway because it helps to make things a bit clearer, I think. Treating that a bit like a fraction, we can say du equals 2 dx, right? Or alternatively, we could say dx equals a half du. Same thing, right? So we're kind of pretending that the dx and the du are variables. Okay. Now this doesn't really, mathematically, this is not really proper notation, but it's accepted as an abuse of notation, meaning that even though this isn't really a fraction, if you treat it like one, it will still always work and it will still help you solve the problem. So now what we're going to do is replace dx here with this half du, right? So let's do that. So that dx goes away and it now becomes a half du. And now I'm going to just rewrite this a little bit. I'm going to take a half out, that half out, and also this half out here, this over 2. So then I've got a quarter on the outside of my integral, and it's just u minus 5 times u to the half du. And that is the same as the following. If I multiply that out, u to the 3 over 2 minus 5 u to the half. And now we can integrate it, right? This is just a standard integration of a variable to a power. So I've used up quite a bit of space here. Let's go over there. So we've got a quarter of, add 1 to the power and divide. So we've got 2/5 u to the 5 over 2. Add 1 to the power and divide. I end up with 10/3 u to the 3 over 2. Yeah, which gives me 2/5 times a quarter, so that's 1/10 u to the 5 over 2, minus 10/3 times a quarter, which is 5/6 u to the 3 over 2. Okay, let me just make a bit more space. We haven't finished yet though, because ultimately we want it all to be turned back into x's, right? So we used our substitution, we got the integral, and now we need to sub back in again. Before we do that, it might be good to factorize this a little bit, because I think these both have u in common, don't they? So this really is u times 1/10 of u to the 3 over 2 minus u to the half okay, so I did just check actually, and unfortunately that's not going anywhere. That we can't really make this any simpler. So we're just going to have to stick with what we've got and just substitute u in directly. So we'll have 1/10, replace u with 2x plus 5. Remember, that's what we originally defined it as, to the power of 5 over 2, minus 5/6, 2x plus 5 to the power of 3 over 2. And that's it, we did it. So the integral of this is all that, with the all-important plus c. Okay, without substitution, this I can't really see how we would do this. Okay, so substitution turned it into a form which we could integrate, which was this one here, and then we just plug the substitution back in at the end. Okay, so this is really demonstrating a general principle of mathematics. I'm just going to clear the screen now, and we'll just try it now with this alternative version of a substitution, and we'll see how that one works. Let me just fast forward with the rubbing out. Okay, so we're going to use this substitution, and before we even use it, let's just immediately do that differentiating that I talked about, right? So we've got u squared equals 2x plus 5. Let's differentiate both sides, and in this case we're going to have to use chain rule a little bit, right? The right hand side with respect to x is easy, that's still just 2, but the left hand side, by chain rule, if I differentiate u squared with respect to x, I'm going to get 2u times du over dx. Okay, so that actually just implies that u times du over dx equals 1, right, if I divide both sides by 2. So we're going to keep that in mind, and now we're going to do the substitution. Let's do it over here and see what our integral becomes. So if u squared equals 2x plus 5, then this is going to become the integral of x times the square root of u squared with respect to x, which is the same as the integral of x times u dx. And now we're going to want to change this x as well somehow. So let's rewrite the substitution as u squared minus 5 over 2 equals x. Yeah. So now we can rewrite this integral as the following: u squared minus 5 over 2 multiplied by u times dx. Okay. And now we need to think about how we're going to change this variable. So how are we going to do this? Well, over here we can say, if we abuse the notation, u du is equal to dx, right? If I multiply both sides by dx. So this dx here, let's replace it with that dx there, and we'll end up with the following: u squared minus 5 over 2 times u times u du. So really this ends up becoming that u times u becomes u squared and then du. And then let's make this a bit simpler. Let's take the half on the outside, multiply it through by u squared, and we get u to the 4 minus 5u squared du. And the integral of that is as follows. And as we can see, this is starting to look a little bit similar to our previous sort of version of trying this. Let's just make some space here. So we've integrated the u version, technically with a plus c. Let's write it out in full. It's a tenth u to the 5 minus 5/6 u squared plus c. And again, we can plug the u squared in and rewrite this as 1/10. And now let's write this as u squared to the power of 5/2 minus 5/6 of, well, it's just u squared, isn't it? Plus c. I've made a mistake. Sorry, no, that is u squared. I have rushed. Sorry if you asked me about it before you got this far. It's u cubed here, isn't it? Yeah, that's the power added, u cubed. So this is u cubed, so then we're going to have to put hang on, if that's u cubed, then I'm going to want to, sorry, not u cubed, so I'm going to make that u squared, but then to the power of 3/2, turn it back into u cubed. That's it, that makes sense. So that now, going down here, is a tenth of, and we replace the u squareds with our substitution, is 2x plus 5 to the 5/2 minus 5/6 of 2x plus 5 to the 3/2 plus c, and it's the same answer, isn't it? Yeah. So regardless of the substitution, we ended up with the correct answer. Obviously, if you use a completely wrong substitution, you just wouldn't be able to get to an answer. But any substitution will technically work in terms of mathematically. Okay, the substitution does not change your answer. It just dictates whether or not you can get to the answer or not. I think in this case, both methods are probably equally difficult. I wouldn't say one was simpler than the other. Perhaps A is a little bit simpler because you don't have to make use of the chain rule. There will be occasions though where one substitution might be more complicated, so just keep that in mind. Let's look at one more example and then you can try some questions. Okay, so in this one, and this is a common application of integration by substitution, we're going to be looking at trig functions, and part of the reason why it works so well with these kinds of functions is that the derivatives of trig functions tend to be other trig functions. So when you do the change of variable, which is the dx changing into the du, it can sometimes cancel out quite easily or quite nicely. So this will probably be an example of this. So there's the substitution, u equals sin x plus 1. Let's immediately do the differentiation so we can have our change of variables handy. Du over dx is equal to just cos x. The 1 goes to 0. And in fact, I'm going to, because it works out quite nicely here, I'm going to show you another method for doing the change of variable, which is not to split up the du and the dx. So like I said, we can write it like this, but sometimes you don't even have to do that. And we'll see in a moment why. So let's look at our integral and do the substitution now. So we've got cos x times sin x times 1 plus sin x cubed. I'm going to change that now to u cubed dx. Okay, and I'm just going to rewrite this slightly so that the cos is at the end. Oops. And let's keep these things in brackets so we don't get confused about what's being multiplied. So we've got cos x there and then dx. Okay, now this with respect to dx, in some sense, it's kind of multiplying this expression. So what you can do is you can actually just replace this cos x directly with this du dx and then cancel out the dx's. So let me show you what I mean. There we've got cos x, and we've just found out cos x is du over dx. So let's replace it. Replace cos x with du over dx. Okay, and then what you can do is you can say, well, du over dx times dx is just going to cancel these, and now I'm just left with du. So this is another way you can do it, and it's equivalent to what we did earlier, where we split up the fraction. So you just end up with this, which is quite nice. And then the final bit of awkwardness is that there's an x here, which we don't want things in terms of x, we want them in terms of u. However, it's very easy to manipulate our substitution so that it's an expression equating sine x. So if u equals sine x plus 1, that implies that sine x equals u minus 1. So we can plug that into here. Sine x is u minus 1 times u cubed du. And this is looking really beautiful now. It's a really simple integral, u to the 4 minus u cubed. So it's 1/5 u to the 5 minus 1/4 u to the 4 plus c. And then we just have to put our x back in again. So u is sine x plus 1 to the 4 in this case, and minus 1/4, and again sine x plus 1. It's not to the 4. What am I talking about? It's to the 5. And then sine x plus 1 to the 4 plus c. And that's it. We're done. That's the integral. So in analogously to chain rule, we kind of have this property where our substitution is being multiplied by its derivative. So you can see we have this 1 plus sine x, and this we could substitute easily because it's the derivative of the substitution ended up being cos x, which was part of the expression itself. In some ways, I would say reverse chain rule, now that I'm thinking about it a bit more, reverse chain rule is kind of like a simple integration by substitution, but it's considered sort of simple enough that you wouldn't actually explicitly write a substitution, but you can think of it that way. So it's quite natural that we learn integration by substitution after reverse chain rule, because it's a kind of more complicated, more formalized, however, version of reverse chain rule, where we do a substitution and then we take the derivative of that substitution and we use it to change the variables. Cool, so let's try some questions ourselves. I'll just take you to them now. Okay, so there's a lot on this page. I don't think you necessarily have to do them all. There's one second slide, and on that second slide are just two very short but tricky questions. So what I think you should do is try some of these in number 1, try a few in number 2, but just give yourself a bit of time to then look at the questions on the next slide. If you feel like you need to practice all of these, then that's fine. Then don't rush yourself. But if you've tried 2 or 3 of part 1 and you feel like you're getting it, then try 2 or 3 in part 2, and then you can move on. But if it's a bit too tricky and you feel like you do need more time, then just focus on doing these. So I leave it to you. Okay. Most important though, as always, if you're not sure and you're getting stuck, just ask me and I'll help you. Okay. So I'll pause now before I go to the next slide. Okay, and there you've got some trickier exam style questions. See how you do.